faithfully delivering value, sharing insights from great books worldwide. Hello, I'm Sally, and this is the Book Club. Today, the book we're exploring for you is The Secret of Water. From leftover droplets on the dining table to shallow puddles at the doorstep, and even to the fierce waves of the Atlantic, water is everywhere. Because of this, we've long taken water for granted. However, in the eyes of British navigator Tristan Gooley, water is incredibly magical. As he puts it, if there's any magic in the world, it must be hidden in water. Gooley's idol is a captain named Abu Hara. Over 1,000 years ago, Abu Hara could predict typhoon paths 2 or 3 days ahead by deeply understanding wave changes and preparing accordingly. With this skill, he made 7 incredible journeys from Europe to the Eastern continent. This ability to read water didn't come from books or classrooms, but from wisdom gathered day and night on the sea. This is the quality Gooley admires most, learning and understanding water through firsthand experience. To satisfy his curiosity about water, Gooley sailed across the Pacific and went to the Arctic to observe ocean currents. Meanwhile, he'd crouch at his doorstep to check road puddles and scramble up and down hills by his backyard pond to watch watercolor shifts. Gooley, who champions hands-on learning, is a member of the Royal Institute of Navigation and the Royal Geographical Society with solid geography theory and has published several top-notch natural observation books. To help more people experience water's joy, he wrote this book, The Secret of Water. The book covers everything from watching a single water drop change shape to describing Pacific storms. In this session, we'll share 3 key angles from it. The secrets of water are its power, its movement, and its color. First, let's discuss water's power, which falls into microscopic and macroscopic types. Water's microscopic power is surface tension. It shows up even in a tiny drop. During the Renaissance, the great artist Leonardo da Vinci was totally obsessed with watching water droplets. In a 1508 manuscript, Da Vinci detailed a drop of water. He noted how it drips from a branch tip. When the drop gets big enough to fall, it always faces some resistance and stretches into an elongated shape. When a water droplet is too thin to support its own weight, it'll fall. The reason behind this phenomenon is surface tension. A water molecule consists of 2 hydrogen atoms and 1 oxygen atom bonded together. And the hydrogen atoms in one water molecule are attracted to those in adjacent molecules, forming a network of mutual attraction. This attraction is the origin of surface tension, and we've long taken it for granted. If you accidentally spill water while drinking, you'll notice droplets form a slight dome instead of spreading flat. That's surface tension at work. Gravity pulls water down to flatten it, but tension stops that process. Of course, surface tension isn't just for droplets. In summer ponds, you'll see insects staying on the water's surface and walking on it. They don't sink because water's surface tension supports their weight. Similarly, molecular attraction gives water another force: capillary action. We learned about this in elementary school textbooks. For example, when dipping a calligraphy brush in ink, even if only the tip touches, ink climbs up the bristle gaps. That's capillary action. Capillary action has 2 steps. First, bristles attract surface water molecules upward. Then, those molecules pull the water below, lifting the whole body. Capillary action is vital for plants, from small grass to giant trees, to extract groundwater and send it to leaves. And it's not just plants. It also affects some things we usually overlook. When in the wild or countryside, you often see muddy banks along small rivers or streams. You might think the river wets the mud. Actually, no. If you look closely, the moist soil is higher than where the river can reach. This is where capillary action plays a role. This mud is a mixture of sand, soil, and air. Their internal microstructure resembles a tiny honeycomb full of cavities. Through capillary action, river water enters these cavities, moistening different soil components and causing varying water rise heights. If soil particles are fine and smooth, like those in clay, water rises significantly higher. In sandy soil, water rises less, while in pure sand, it barely rises at all. Additionally, air pressure affects capillary action in soil.
Before storms, sudden pressure drops reduce soil's capillary absorption, causing water to flow back into streams and rivers, increasing flood risks. In short, seemingly weak surface tension and capillary action profoundly impact both ecosystems and human society.
For water, greater macroscopic power comes from flow impact. It's kinetic energy. Physics tells us water's kinetic energy relates to its mass and velocity. When passing a stream, it's hard to imagine its true power. A simple calculation shows a 1.5-meter water cube weighs up to 3 tons. Thus, even a gently flowing stream can dramatically reshape riverbanks over time. What details can we observe in rivers? First, natural rivers never flow perfectly straight forever. Typically, rivers flow straight for no more than 10 times their width. Aerial views of the Yellow River's winding bends make this phenomenon strikingly clear. Any river flowing straight over long distances must be artificial. Fascinating phenomena often occur at river bends. On the outer bend, water flows faster. Faster flow means stronger impact. Conversely, on the inner bend, flow slows. Sediment deposits more easily there. Day after day, year after year, the outer bend erodes riverbank soil, which then deposits downstream on the inner bend. This gradual accumulation of outer erosion and inner sedimentation transforms both riverbanks into completely different landscapes. Generally, the outer bend gradually develops a vertical, cliff-like bank that recedes over time, while the inner bend forms an expanding gravel bar or mud flat. If you ever gaze upon a great river, observe nature's incredible craftsmanship. We should understand more about rivers. Humans are fragile against water's force. Especially when wading across, always watch for changes in current speed. Regardless of river size, notice different flow speeds between center and banks. Slower flow near banks has 2 causes: friction with the bank and shallower depth. Additionally, shallower water near banks means slower flow. Typically, bank flow is just 1/4 the speed of mid-river currents.
So, when crossing, though you might manage near banks, never let your guard down.
Mid-river currents will likely knock you over. Moreover, with increasing extreme weather globally, flood threats intensify. We must learn to assess extreme weather's impact on rivers. For example, how does a nearby river change after heavy rain? You might think it's simple. Water levels rise, and you're not wrong. But river-rain relationships are more complex than we imagine. After heavy rain, some rivers sweep away cars while others barely rise. Why? It actually depends on land conditions near the river. Soil can be roughly categorized as permeable or impermeable based on water absorption. Impermeable soil, as the name suggests, won't absorb surface water. Clay is a classic impermeable soil. Rain on clay stays on the surface, flowing directly into streams and rivers. While chalk and limestone are common permeable soils, rain falling on this soil seeps underground, becoming part of the groundwater. Comparing both, rain on clay makes local rivers rise within hours, but the same rain on chalk rock might not noticeably affect local rivers for months because the water gathers underground. In the author's English hometown lies the River Auk, surrounded by clay. That's why this river's flow changes extremely. After heavy rain, its peak flow can be 1,000 times its lowest normal flow.
So, if you live by a river, pay close attention to nearby soil. Prepare for once in a century downpours. From a drop's tension to a river's kinetic energy.
These forces work together, shaping water's movement. Whether ripples in a teacup, pond, or ocean waves, all move as water waves. In part 2, let's explore wave motion characteristics. Meet different kinds of waves. The first wave feature, up-down motion. Waves transfer energy from place to place. Some mistakenly think waves involve water moving horizontally. Actually, that's not true. Imagine shaking a bed sheet. Energy travels from your hands to the other end, making a whip-like sound. The sheet doesn't move horizontally, just vertically up and down. Similarly, tossing a stone into a still lake creates ripples. Focusing on one wave creates an illusion of forward motion. But watch a floating leaf. It bobs up and down without moving forward. Beyond up-down motion, each wave has unique traits. To describe wave behavior, let's cover basic terms. First, the wave's highest point is the crest. The lowest is the trough. Wave height is the trough to crest distance. The distance between adjacent wave crests is wavelength, and the time for a wave to travel between crests is its period. Remember these terms. Let's analyze how wave period is one of water's most distinctive features. Tiny ripples in teacups have short lifespans, with periods under a second. But a wave in a bathtub might have a 1 or 2 second period, crossing from end to end. Of course, studying cup or bathtub waves is small scale.
What's truly fascinating is ocean wave motion. Those sea swells.
The author spends pages teaching wave identification. Each crest hides mysteries that spark curiosity. Some say no wind, no waves. Others claim waves rise without wind, which is true. If a Brazilian butterfly's wings can cause a North American storm, does this butterfly effect exist in waves? If I create waves off Hong Kong or Xiamen, could they reach the US or Australia?
Even form giant waves there?
To solve these puzzles, we must understand wave origins and transformations. Wind indeed creates most waves. It's the primary cause. As wind blows over water, friction transfers energy, forming waves. So no wind, no waves is mostly correct. But waves also form from other sources. Lunar gravity, undersea volcanoes, earthquakes. The moon's gravity pulls seawater, causing tides.
Earthquakes unleash instant energy, creating massive waves or tsunamis.
Beyond these, can waves truly appear without wind? Yes. Even ignoring quakes or the moon, windless waves can occur. This relates to wave properties themselves. Next, let's detail ocean surface waves. By size, there are roughly 3 types: ripples, wind waves, and swells. Surging swells evolve into wind waves, which may further become swells. This describes their relationship. Like seeds, saplings, and towering trees, the smallest waves are ripples appearing with a light breeze. These ripples are nicknamed cat's paws, as if an invisible cat is pawing at the water. Ripple formation is a tug-of-war between surface tension and wind force. Wind tries to ruffle the surface while tension smooths it. Both shape ripple patterns. Study directional wind, sustained over time, involves ripples into wind waves. Wind friction is minimal on calm water, but ripples create surface roughness that increases friction. With sufficient wind duration, ripples transform into wind waves. Once wind waves form, surface tension's stabilizing effect becomes negligible. Unchecked by tension, wind waves travel considerable distances. Before vanishing, they transmit energy kilometers away. Stronger, longer-lasting winds build higher energy waves called swells, far more powerful. Swells persist beyond wind zones, crossing oceans for thousands of kilometers. Seeing swells from an ocean liner might seem like windless waves, because their wind source is distant. This incidentally answers the wave butterfly effect question. Swells created off China's coast could indeed reach the US. There's no precise boundary between these wave types, but we categorize roughly by period. Ripples, less than or equal to 1 second, swells greater than 10 seconds, wind waves in between. All 3 coexist. Swells lasting days can host new ripples and wind waves atop them.
Undoubtedly, the movement of waves greatly impacts navigation.
For sailors drifting at sea, recognizing ripples, wind waves, and swells is an essential skill. And in the eyes of experienced navigators, they also assess wave shape, wavelength, and other features to decide how to sail next. In the early 19th century, British navigator Francis Beaufort proposed a scale called the Beaufort Wind Force Scale. This is now the internationally recognized wind scale. Beaufort summarized how wind intensity corresponds to wave patterns so sailors can predict sea conditions and prepare. At Beaufort Force 5 or below, waves are calm with white foam crests, so fishing boats can sail safely. When wind hits Beaufort Force 6, Waves produce large white foam areas and splash with spray.
At this point, fishing boats should only hoist half their sails and focus on safety.
Of course, water can carry a boat but also capsize it. Without professional training, ordinary folks shouldn't try to fight water's power. For most people, the best relationship with water is quietly admiring its beauty, especially its ever-changing colors. Understanding water's color involves three angles: how water interacts with light, your viewing angle. And third, what's in the water? First, water and light. If you only have a cup of water, it's transparent. Without light, water has no color at all. Light gives water its color, and this interaction depends heavily on the water body's size. If you have a large white bathtub, while filling it, you might see that with just a few centimeters of water, it looks transparent, like in a cup. If you keep the faucet running, water flows in and the tub's level keeps rising. Then you might notice a faint bluish-green tint in the water. If you look at a swimming pool, this effect becomes even more obvious. As the water body gets larger, its color appears bluer. Pure water is colorless, but it absorbs some light. When white light enters water, some reflects while a small portion gets absorbed by water molecules. We all know white light combines many colors, and water absorbs them unevenly. Red and yellow light get absorbed more easily than blue. This means the deeper light travels, the more red or yellow gets absorbed, leaving blue light to reflect back, making water appear bluer at depth. This simple principle gives captains a vital skill, judging safe routes by watercolor. Their eyes become hypersensitive to blue, detecting the subtlest variations. After years of training, navigators spot thin dark blue lines indicating deepest channels, navigating safely through treacherous reefs. Sometimes, even advanced tech can't match an experienced local sailor's accuracy. Beyond water's physical interaction with light, your viewing angle affects perceived color. Standing by a clear pond, looking straight down, you see reflections, fish, underwater plants, everything. But step back 10 paces, and everything vanishes. You might not even see water at all. What you perceive now are only reflections from the opposite shore. The same water surface shows completely different appearances when viewed vertically versus at an angle. And often we think we're observing water, but are actually seeing reflections of distant objects. And like gazing at the horizon where sea and sky blend into one, the ocean color you see then is actually determined by the sky's color. Blue on clear days, gray when overcast. You're not so much observing water as looking at the sky. Plus, what's in the water affects its color too. In shallow water, everything beneath influences its apparent color. This makes sense. If there's a white beach before you, the shallowest seawater appears white. Further out, the water takes on a pale, faint blue hue. Look even farther, and the blue gradually deepens until the white sand no longer influences the water's color. Near golden sand or pebble-covered shores, water at the same depth appears bluish-green. Beyond sand and rocks below, water contains countless particles. Even seemingly clear sources have microscopic impurities like dust, plankton, and bacteria that alter its color. Sediment makes river water murky, tinting it light brown. But this brown varies subtly depending on regional soils and river flow rates. In Borneo, Indonesia, the Dayak people navigate complex waterways by distinguishing these sediment color variations. Sometimes sediment even creates unique beauty. Glacial lakes contain rock flour, fine particles from glaciers grinding rocks. These particles turn lake water a bright, pale blue. Travel to northern Europe to see many lakes with this hue. Besides sediment, water often contains algae whose growth depends on nutrient levels. Excess nutrients cause eutrophication. Algae then bloom massively, creating green algal blooms.
One distant glance reveals this green water is hostile to other life.
Blooms drastically reduce sunlight and consume dissolved oxygen, suffocating other organisms. Algal colors vary. Dunalia salina thrives in salt lakes, turning them pink. The opposite, oligotrophication, occurs when nutrients are scarce. Algae struggle to survive. The classic example is the Mediterranean, with super low nutrients, so algae barely grow, making the water crystal clear and attracting tons of tourists. In short, watercolor changes depend on light, viewing angle, stuff in the water, and more. Next time you're admiring a lake or vacationing by the sea, get a first-hand look at those magical, shifting colors. Finally, about watercolor, let's add a life-saving tip.
If you're hiking in mountains and a clear stream suddenly turns muddy, get away from the riverbank fast. It means disaster weather upstream.
Sediment's washing down, and a flash flood is likely on its way. So far, we've covered basic stuff like surface tension and capillary action, learned how to tell waves apart, and figured out why watercolor changes. Of course, humans haven't fully cracked water's secrets. Many puzzles still baffle us today. Like, at the microscopic level in living things, how do molecules like proteins interact with water molecules? Or at the macro level, how to predict floods and tsunamis better? These all need deeper digging. Exploring water not only helps us understand this life-giving stuff, but also sharpens our knack for cracking nature's codes. And it's an absolutely amazing feeling. All right, that's the wrap up for The Secret of Water. Reading notes are below the audio. See you next time.